Hello and welcome back. In this video we'll focus on explainable AI, in particular about black box and white box models. So let's recap the approach in machine learning in general. We start with data, either tabular data or unstructured data like text or images, put this into a machine learning model and out comes a prediction, for example a classification result or regression result. And many of the powerful methods that we have are black box models, so we don't really understand how each individual prediction was made. We know how, at least in principle, the neural network works, but we can't really trace back how a single prediction was made. These methods are typically very powerful, but we don't really know what the model learns. So we need to understand a bit in more detail how what the network does, for example, is connected to our domain expertise, and this is the topic of explainable AI. So why do we need to do this? There may be regulatory requirements by law. For example, in banking or medicine or finance, you will find yourself in a situation where each decision that affects a human needs to be explainable. There is also the Swiss and European data protection law. There is no explicit requirements, but several of the paragraphs in there essentially force you to do explainable machine learning if your decision affects humans. But also in all other applications you want to build trust in AI systems. For example, if you have operational decision in your business, in medical AI, if you want to base a treatment based on AI, you want to understand why a given treatment was suggested. But also if you conduct your experiments in engineering, you want to understand how a given prediction was made. So there are several explainable approaches. We could have a focus on the features, so we understand the importance of each feature and the causal significance of each feature. We could move to a white box machine learning model, or we could explain each prediction. That means we build locally faithfully surrogate models or replacement models. That means that we don't understand how the model itself makes all the decisions, but we can build a sort of approximate model around each decision and understand this. It's the usual conundrum, really. We have a complex domain, a complex problem, so you want a very performant machine learning algorithm. These tend to be black box models, but they should also be explainable. Let's start with the features. In particular, we start with feature importance. Here we understand the algorithm's behavior by looking at the features and how important they are to make a prediction. One of these approaches is feature permutation importance, or mean decrease accuracy. This follows an idea originally developed by Breiman, and the idea is that we observe how much a score changes when a particular feature is removed or its values are shuffled. The drawback is, of course, that we need to train a new model for each of these permutations. The alternative is that we permutate on the test data and use the full model that is trained on the full data. It's not ideal, but because typically we use a lot less test data, that tends to be fast, and also we don't need to retrain. You can also use Shapley values. They originally come from game theory, and the general idea is the following. We can compare it, for example, to a football or soccer game, and each feature is now a player in this team. And the idea is to quantify how much do each of these players, in our case here the features, contribute to the outcome, the prediction. Now we use different combinations of the features, and that influences the quality of the prediction. Think about it in the same way as if you were building a team on the football pitch, and you as a coach or trainer will put different players on the field depending on their abilities, not only their abilities by themselves, but also how well they play together. And the idea of the Shapley values is sort of transfer this general idea to features in machine. There's a separate notebook where we explore this for wine quality and we can see how the features relate to each other. You can also do a partial dependency plot, and these visualize the dependency of a feature on the prediction. For example, if we have numerical features, right, then we look at how the outcome changes as we move across the numerical values. And this can give us another insight of how the feature behave and how it affects the performance of the algorithm. A completely different approach would be to use white box models. They are intrinsically fully explainable, hence the name, so we can understand both how the model works and each prediction. Simple approaches for white box models are the humble linear regression, but also a single decision tree, at least if it doesn't become too complex, or logistic regression. However, the disadvantage is that they are typically not powerful enough. What we can do is move to so-called generalized additive models. They are sort of, if you want, an extension to linear regression. They tend to have good performance and they are almost as explainable. As you can see, the formula for such a generalized additive model is very much resemblant for linear regression, but it's slightly more complicated. So we don't work on the target variable y directly, we use the expectation value for it, and we also modify it with a so-called link function, so we move it to a different space. And then we have the terms that are really the same as linear regression, slightly more complicated. In linear regression, for example, we would only have the variables xj. Now we modify this and apply a certain function to each of them, so we make it a bit more general. We can also include pairwise interactions with two features, so this gives another level of complexity. It maybe reduces slightly the explainability, but gives us more power in the predictive part. The last thing we can discuss are surrogate models. The key idea is here that for each prediction we build an explainable model. This can explain a single prediction, but it cannot explain the whole model. It's maybe in a sloppy kind of way. We build linear regression around each prediction, and then we can understand what this does. This doesn't explain the whole model, but we can use it, for example, with a powerful black box model, and we can explain how each decision was arrived. We can use this, for example, for image explanations. We have there multiple approaches. We can use image occlusion. This is pretty much resemblant to feature pigmentation importance, where we obscure parts of the image and observe the change in the outcomes. We can have saliency maps and highlight pixels that are relevant for the predictions, or we can reverse the convolution in neural networks. Right? Or we can build these surrogate models and say which part of an image are most dog-like and build locally explainable models. We can also understand a bit more how neural networks learn by looking at the different ways a network is composed. For deep convolutional neural networks, they generally work the way that the lower part of the network, or the first few layers, these are filters that learn image features, and the later part of the network are then to do with the classification, like which kind of dog there is. So if we visualize the activation function, we can understand in a bit more detail how such a filter was learned and what these different filters are about. A different approach yet is to use counterfactuals. Here we explore the model behavior by changing the inputs and observing the change of output. It's really answering the question, what happened if I did the following thing? We can, for example, select a data point and then find its counterfactual. That means we find the data point that has the most similar feature values, but has the opposite outcome in case of a binary classification. And that also gives us an understanding of how sensitive a model is to the values of specific features, and, for example, where decision boundaries lies and how they are affected.